Okay, any questions? Any problems you want to look at before we get started here today? Okay, all right, let's go ahead and get started then. This week we've been speaking about the quantum mechanics, the structure, the electronic structure of the atom. We're not that concerned with the structure of the nucleus, but we are concerned with the structure of the electrons, because the electrons are the particles that are responsible primarily for chemical reactivity and chemical structure. So we want to know about them. So here's what we'll do. We'll take a look at what we have so far. We have this idea that the electron exhibits this behavior, which we call wave-particle duality. So it's both. It's a wave and it's a particle. So it behaves like a wave under some circumstances, and it behaves like a particle flying through space under some other circumstances. And so it turns out that when you have such small particles or such small waves, they're limited by the Heisenberg uncertainty principle, which essentially says that we cannot, there's a limit to how well we can know or understand the speed and the position of a subatomic particle. So we have a limit to the accuracy in speed and position of the electron. So what we do is we use what's called wave mechanics. And wave mechanics is predicated on the following idea. The electron is a wave. We know that it is somehow related to the nucleus. So here's the nucleus here at the center. We know the electron is some wave that is interacting with that nucleus because it's attracted to the nucleus. The nucleus is positively charged and the electron is negatively charged. So there's some interaction occurring there. There's an attraction that's occurring. And so by applying wave mechanics, what we get are certain shapes and energies. So we get energies for the electron. And this goes for any electron in the atom. We could have one electron or two electrons or three. Each electron will have a certain amount of energy. And the amount of energy is determined by this quantum number, which we call the principal quantum number. Okay, it's called the principal quantum number. And this quantum number takes on the values 1, 2, 3, 4, 5. And so we can draw a little energy level diagram indicating that at the lowest level, by the way, this is closest to the nucleus, n equals 1. There's a certain amount of energy. If the electron is in the n equals 2 level, it has more energy, right? So this is further from the nucleus. And so forth and so on. N equals 3, n equals 4, n equals 5. And you go as far as you want. Okay. Notice that the energy spacings do get closer and closer to each other. They converge, meaning they're getting closer. The distance between 1 and 2 is much larger than the distance between 2 and 3. Okay. So that's called the principal quantum number. Gives us the energy of the electron. The second one is what we'll call the shape of an orbital. Okay. And this is given by the quantum number L, which can be 0, 1, 2, 3, so forth and so on, all the way up to n-1. It's limited by n-1. Cannot be as large as n. It has to be smaller than n. And this is often referred to as the angular momentum quantum number. And there's a notation for this one. The notation is that if L is equal to 0, we call it S, an S orbital. If L is equal to 1, we call it a P orbital. If L is equal to 2, we call it a D orbital. And if L is equal to 3, we call it an F orbital. Okay. Now, this idea of the orbital is the following. It turns out that if you have a wave, and the electron is a wave, it's very difficult, if not impossible, to really develop any physical intuition to what that means. We don't really understand what it means to say that a particle has a wavelength in a sense. So what's done is a little trick, and the trick is essentially mathematically, if you take a wave and you square it, so if you take a wave mathematically and you square it, you get what's called a probability, okay, a likelihood. So the orbital is not really the wave itself, it's the square of the wave. And so what you get is this. It turns out that for certain L values, if L is equal to 0, if you take this wave and you square it, you get a probability distribution, the likelihood that an electron is somewhere around the nucleus. So we don't know where it is, we just know it's somewhere around the nucleus. And so you end up with this particular shape. You get this shape, it's kind of interesting. It looks like a sphere, like a ball. And it's a probability distribution. And so this is what we call an S orbital. And this is for the case where L equals 0, right? Remember, here's our notation here, SPDF 0, 1, 2, 3. So that turns out to be the more up-to-date understanding of what an electron is. It's a charged particle, a negatively charged particle that exists in a space around the nucleus with particular shapes. And here's one of them, we call it an S orbital. So that's a shape. Now, if n increases, so I'm going to say this is n equal to 1, what happens is, again, there's the nucleus at the center. The shape doesn't change if n gets larger, but the size gets larger. So energy and size are connected to each other. The larger the n value, the more energy the electron has, but also the further away on average it is from the nucleus. So see how this one's larger? This is still called an S orbital. It's the same shape, but L is equal to 1. I'm sorry, L is equal to 0, but n is equal to 2. So if n increases, not only does the energy increase, but the size of the orbital increases. So what we're doing here is we're giving up the idea of saying where exactly is the electron. Remember, we can't do that according to the Heisenberg uncertainty principle. We don't have that kind of information available to us. But we can talk about the likelihood of where it is, the probability of where it is. So imagine that you're in a big, busy train station like Grand Central. We're essentially saying, look, you can't know exactly where a particular person is, but you can know the general area of where they are. They're somewhere in this station. You've lost the information of where they are exactly, but you know they're somewhere. And there's a likelihood they're near, you know, the entrance to the railroad tracks or something like that. So if n gets larger, the probability distribution gets larger. So that means where the electron is increases, right? The area or the volume that it has available to it. So the reason I'm drawing these little dashed lines is because we're claiming it's somewhere in there, somewhere in that region. And so again, this is still an S orbital because it has the same shape. It's essentially a little ball. And if it's an S orbital, L is still the same, it's 0. But now n is larger. Now we're saying n is 3, right? So it's larger, more energy, larger energy, but also a larger orbital. So the electron is somewhere in this region as opposed to the other two. Now, what happens is it gets a little inconvenient to draw these dashed lines. So typically what people do is they just draw one circle. Okay. They just draw one circle to say it's somewhere in that region. We don't know where it is in there, but it's somewhere in there. Now, in fact, because it's a wave, really what it is it's spread out. Remember, waves can spread out. Like if you look at a water wave, like on the ocean, there's no like, this is where the wave is. The wave is spread out over a long region, a large region. Same thing here. The wave is spread out over this region of space. And as n gets larger, the volume increases, right? As n gets larger, the volume of this orbital gets larger. So you should remember two things about these, or a few things, but two important ones is if it's a sphere, that's an s orbital, right? And if n gets larger, the size gets larger, but also the energy gets larger. So an electron has more energy if it's occupying a larger volume than it does if it's occupying a smaller volume. Okay, so that's the s orbital. But there are other types of orbitals too. They're related. We also have what's called, so we have the s orbital. And I'm just gonna, show again. Here's your 1s. Here's your 2s. They're a little more complicated than I'm drawing here, but close enough. And again, you can go as far as you want. N can go all the way up to infinity. Okay, 4. Remember that the number is referring to the quantum number n. So 4 means n equals 4. 5s. 6s. They're kind of cool. So the electron's occupying this space. Again, the little dot at the center is the nucleus. The nucleus is tiny. It's this little dot, little speck at the center. Okay. And again, for all of these, you know what n is. Because the notation, this orbital notation, tells you what n is. That number in the front is n. But the letter also tells you what L is. These are all L equals 0 because they're all S. Oops, sorry. My brain has a tendency to increase numbers like I'm counting. There we go. They're all L equals 0 because they're S orbitals. But we also have what is called a p orbital. And p, that's that notation, L equals 1. Okay, so if you see the letter P, you immediately go L equals 1. By the way, the notation is lowercase, so not uppercase s, not uppercase p, it's got to be lowercase. Uppercase s, p, d, f means something slightly different, and so we use lowercase. Okay, so the p orbitals have different probabilities. These are waves. So imagine, again, like a drum membrane vibrating, right? It's vibrating up and down as you beat the drum. There's a wave being set up in that membrane. Imagine the electron as a wave that's vibrating, inherently vibrating. It has this wave. It's kind of a weird thing because the things we normally deal with in life are not really vibrating, but it's a vibrating object, a vibrating particle. So the probability distribution looks something like this. Again, I'm not going to draw the little dot, 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 dot. I'm just going to go straight to the sort of circles. So the nucleus is at the center, right there. Again, it's this tiny, tiny dot. The p orbital looks something like that. It's different. It's got 2 lobes. It's got 2 parts to it. So this is called a p orbital, okay? And the thing about the p orbitals is that you cannot have n equals 1. It only starts at n equals 2. So you can only have p orbitals from n equals 2 or higher. And again, it's a p, so L equals 1. So this one would be called 2p, right? You do the quantum number, the principal quantum number n, so that's the 2, and then you say, oh, it's got this shape, so that means it's a p orbital, which also means that L is equal to 1. So the shape tells you what L is. You can also have n equals 3. And what happens here is just like with the s orbitals, it gets larger. So a 3p is larger than a 2p. Again, it's a p. You recognize the shape is what you do. You say, look, oh, I see 2 lobes. I recognize that as a p orbital. And then you say, if it's a p, that means that L is equal to 1. From the shape, you really can't tell what n is. There's no way to tell from the shape what n is unless you saw them all kind of next to each other. But this would be a 3p because just like the s orbitals, as n gets larger, the size gets larger, the size of the orbital. So what we're claiming here now is that if an electron is in one of these orbitals, it's in this space here, and it's in this space here. So as n gets larger, it's occupying more space. So that's kind of interesting. This is an interesting wave because take a look at it. It's actually got 2 regions of space. So that means it's a vibration that's occurring. The particle is vibrating over both regions at the same time. So it's existing in both of those regions at the same time. It's kind of cool. And then again, you can just keep on going. If n is equal to 4 and it's a p orbital, it would be 4p. And so you just have a larger orbital. Again, the nucleus is tiny. So it's occupying those 2 regions, is vibrating in it. And you can keep going. You can go on to 5p. You can go on to 6p. You can go on even to 7p. But essentially what happens is it just gets bigger and bigger, more and more energy, right? And those are called p orbitals. Now, here's what's interesting about the p orbital compared to the s. The s is a sphere. It's a ball of charge. The p orbital, though, has what we call lobes. Each of these is called a lobe. So the p orbital has 2 lobes. It turns out what happens with these electrons is they start obeying certain mathematical laws that people have figured out. And one of the mathematical laws is that an electron can occupy 3 different types of p orbitals, one at a time. It can't be in all 3 at the same time, but it could be in one of the 3. So what happens is you can have, I'm going to draw an XYZ coordinate system. So X, Y, Z. You can have a p orbital that occupies one direction. So it's in the X direction. But you can also have one. I can't draw them all on the same graph because it doesn't work for me. You can have another orbital that is 90 degrees rotated. I've just rotated it from the X to the Y coordinate, right? To the Y line, the Y coordinate system. And then you can have a third one too. So X, Y, Z. So you can have one that goes along. Oops, sorry. I made a mistake there. That's Y, Z. So this one is a mistake. There we go. You can have one along the Z axis. All 3 are possible. So what that means is if you're talking about p orbitals, you have 3 possible orientations. I'm going to use the word orientation. Maybe you could also use the word direction. Okay. So one of them is pointing in this direction. One of them is pointing in this direction. And then one of them is pointing in this direction. You get 3. It's just mathematically how it works out. And it turns out that electrons obey certain mathematical patterns that we observe. So those are the 3. So they're actually given names. So one of them is called PX. One of them is called PY. And one of them is called PZ. You don't need to know that notation. If you're a chemistry major and you're going to go on, you're going to take more advanced courses like physical chemistry, you would learn more about this notation and about how to compute these things. You actually do calculations to figure out the shapes. But I just want to point out that if you see that notation XYZ, it's referring to the fact that for p orbitals, you have 3 different orientations, 3 different directions. And now here's that third quantum number. The third quantum number is unimportant really for the s orbitals, but it becomes important for the p orbitals. What we said was there was a third quantum number, m sub l, and that m sub l is 0 plus or minus 1 plus or minus 2 all the way up to plus or minus l. And we said the limit was what l was. Well, that's where this comes into play here. For the p orbitals, l is equal to 1. So if that's the case, then the series for m sub l would be 0 plus or minus 1. You would stop at 1 because l is 1. So that means you get 3 values, 0, minus 1, and plus 1. So really what that means then is the fact that you have 3, it shows up in m sub l. Minus 1, 0, and plus 1. There's your 3 right there. It's kind of interesting. It doesn't really matter what the specific value is. So I'm not going to claim that this one has to be minus 1 and this one has to be 0 and this one has to be plus 1. It's arbitrary which one you call it. But the point is that m sub l is telling you how many directions there are, how many orientations. So the fact that you get 3 values tells you there's going to be 3 different orbitals. Okay, so the number of orbitals for the type of orbital is given by the m sub l. It could be 1, it could be 3, it could be 5. See, if it's only 0, that'd be 1. If it was 0 or plus or minus 1, that'd be 3. If it was 0 plus 1, minus 1 plus or minus 2, it'd be 5. So the number of orbitals is given by that m sub l. Okay, so those are the p orbitals, and they are important in the nonmetals. Okay, so we'll see that in just a moment. And then the third type, so we have s orbitals, we have p. The third type of orbital that we'll talk about is called the d orbital. The d orbital is even more complicated looking. Oops. The nucleus is at the center, and there are 4 lobes. So if you see 4 lobes, that tells you right there it's a d orbital. Okay, remember the s orbital is just a sphere. The p orbital has 2 lobes. The d orbital has 4. It's even more complicated. It's a really complicated vibration. And again, it's 3-dimensional, even though I'm only showing you as 2. So again, the d orbitals are L equals 2. And so let's figure out what m sub L could be. The series for m sub L is you go from 0 to plus or minus L. So you're going to stop here. You're going to stop at 2. So how many is that? You got 0, plus 1, minus 1, plus 2, minus 2. That means there's 5 orbitals, 5 directions. Now, I can't show you all 5 directions because I'm not that good of an artist. It takes some pretty good animation to be able to show 5 different directions. But essentially, you get 5 orbitals. So you get 5 of these things. I'll just draw little boxes to represent them. Okay, remember each of these boxes is like some kind of orbital with a different direction, a different orientation. Okay, so the way this would work is you'd have L equals 2 for all of them. And then m sub L is, you can put the number in any sequence you want, but I'm going to go from minus 2 to plus 2. M sub L is plus 1. M sub L is plus 2. Okay. And so there's 5 different orbitals. These are important in the transition metals. Okay. So you got You got the s orbitals. The s orbitals are important in the alkali metals and the alkaline earth metals. Then you get the p orbitals. Those are important in the nonmetals, right? So that'd be like carbon, nitrogen, oxygen, fluorine. Those are the nonmetals. And then the transition metals would be ones like iron, chromium, nickel, silver, gold. Those are the transition metals, all those kind of precious metals that people want. I guess lithium's a precious metal too, but that's where those come up to play. Okay, so let me show you then. There's a lot of background to this. Let me show you a typical type of problem just so that we can go through it. Oh, let's do the... Okay, suppose we have these little sketches here. And we want to indicate what type of orbital is. Could be S, could be P, could be D. So here's the first one. Here's the second one. Here's the third one. And then here's the fourth one. Okay, so let's take a look. And I'm gonna put our little chart down here. The S should be like a ball. The P should have 2 lobes. The D should have 4 lobes. And I don't think that Alex is going to have you do this, but if you see 6 lobes, that's an F. Now, there's one exception to the D, and that is there's a weird looking, one of the Ds is kind of weird looking. So I'm going to put a little box around this. There's one that doesn't have 4 lobes, but it has 2 lobes, and then it has a ring around it in the center, kind of like Saturn, like the planet Saturn. It's kind of weird. And I'm not going to go into why that's all the case, but there's 2 different shapes you'll see for the D, one with 4 lobes and then one with 2 lobes with a ring in the center. Amazing stuff. Okay, so those are your 4 shapes. So let's take a look. Which ones are these? Well, that one right there is a D, right? That's this one right here. So you would recognize that as a D orbital. So you're just determining by the shape. The next one, there is no orbital that we're dealing with that has just a ring. If it had the 2 lobes up and down, then that would be a D orbital, but there's nothing there. So this is not not an S, P, D, F. It's not any of them. S, P, D, F, sorry. It's not any of them. So that one, nothing. Third one over here, oh, 2 lobes. There you go. 2 lobes right next to each other. Now, sometimes the lobes are drawn slightly differently. Sometimes they're as a ball. Sometimes they're like, I don't know, like a bagel, you know. But the point is there's 2 lobes connected to each other. The nucleus is in the center. So that's this one right here. So that's a p orbital. And then the next one, that one looks that doesn't look like any of these. It's not a sphere, right? It's not a sphere like the s orbital. It doesn't have 2 lobes or 4 lobes or 6 lobes, so it's not a p, d, or f. This is actually none of these, but it is actually a real orbital. It's called a molecular orbital, and that's a topic that's covered in chapter 9. Okay, but that's not one we would need to worry about. Okay. So that's one aspect of something you want to do, just being able to recognize these orbitals. Okay. The next type of thing that you want to be able to do is to list the orbitals in the order of increasing energy. So remember what we said here. We have energy. And what I did was I said, you got n equals 1, you got n equals 2, you got n equals 3, and then n equals 4. So as n gets larger, the energy increases. Now, if we're given the notation, so I'm going to give you these orbitals, which are called subshells. Okay, 3p, 3s, 2p, and then 4s. Okay, and these are going to be for atoms other than hydrogen. Okay, so we have, as n increases, the energy gets larger, but sometimes they're the same n. So what do you do if they're the same n? Well, it turns out in general, it goes in this pattern. If n is the same for 2 subshells, the energy goes in this in order. S, then P, then D, then F. And this is the order of increasing energy. This direction. So that means that a 4F would have more energy than, say, a 4D, right? F has more energy than D if the value of n is the same. So what you do is you do the value of n first, and then if it's a tie, meaning they have the same value of n, then P is more than S, D is more than P, and F is more than D. So let's take a look at it here. The lowest one is a 2, so that's going to be the lowest energy right there. The 4, that's a 4, right? So this one's going to be the highest. 4s will be more than 2p for sure. But then you got these two. This is a tie. Okay, so this is going to be in the middle, right? Because it's more than 2, but it's less than 4. So what you do there is you split it off. For 3, the p is more than an s. So you're going to have your 3p and then your 3s. The 3s is lower. So your 2p is here, and then your 4s is here. So here's how you could rank it. You would go from lowest to highest. And the lowest one would be the 2p, because that has the smallest value of n. The highest one would be the 4s, because it has the highest value of n. And then for the 3s, you got a tie for n, but p is greater than s. So it would be 3s and then 3p. Okay, so 2p is less energy, lower energy than 3s, which is lower than 3p, which is lower than 4s. Okay. Any questions on either of those two questions, the shapes or the relative energies? Okay. The actual things you do are not that complicated, but the whole kind of background theory is pretty complicated. Okay. All right. So then really the last thing to do then in this chapter is to take a look at what we call electron configurations. And they're kind of fun. Most people enjoy these. Oops. And there's a couple different ways. There's actually a few different ways in which these are done. One is using what we call box diagrams. And the box diagram essentially shows you using boxes where the electrons are. Okay, so let me give you a couple of pointers on this. Think of an atom as having many electrons. You know, hydrogen only has 1 electron, but helium has 2, lithium has 3, beryllium has 4. So most elements in the periodic table have lots of electrons, meaning more than 1 or 2. Okay, so the question is, where do these electrons go? it turns out there's a limit to how many can fit into an orbital. And so the limit is 2. So one, what we call atomic orbital, those are the orbitals we've been talking about, can have up to 2 electrons at a time. No more than 2. So if I write a 1s orbital, it can have up to 2. Okay. The same is true for a 2p orbital, for example. If I write a 2p, it can have up to 2 electrons. But remember, for the 2p subshell, there were 3 orientations. So for the 2p subshell, the subshell, by the way, is just all of the orbitals with the same value of n and the same value of p. So because these are all n equals 2, and they're all L equals 1, they're the same subshell. So subshell, all the orbitals with the same n and L values. But each one can handle 2 electrons. So if this one can handle 2, and this one can have up to 2, and this one can have up to 2, that's a total of 6. And then remember the Ds. The Ds have 5 orientations. Directions. So if each can have 2 electrons, that gives you 10 maximum, up to 10. Okay, so what happens is, for these configurations, if you have S, you only have 1 orbital, so you can have 2 electrons. If you have P, you can have 3 orbitals, so you have up to 6 electrons. And if you have D, you have 5 orbitals, so you have up to 10 electrons. So in essence, what happens then is these electrons, they start filling up these orbitals in the lower energies up to higher energies. So you get the 1, n equals 1, they start filling with electrons. And then once they're full, then n equals 2 starts filling. So after n equals 1 is full, n equals 2 starts to fill. And then once that's full, then you go up into n equals 3. And this is called the Aufbau principle. Aufbau principle means that it's filling up from lower to higher energy. Okay. The electrons are represented using not a dot, but an arrow. So if you think about it, we've used different ways of representing the electrons. In redox chemistry, we do that. Here, we're going to represent it with an arrow pointing up or an arrow pointing down. Okay, so it's a different notation. The meaning of the up or down is there's a 4th quantum number for the electron. If it's up, that quantum number is +1/2. If it's down, it's -1/2. Now, people generally don't like to quote what the actual value of the quantum number is, because that's kind of tedious. So usually people will just say, hey, if it's pointing up, we call it spin up. If it's pointing down, you call it spin down. So that's an easier notation than wearing +1/2 or -1/2. Okay, so now let's get to the box notation. What happens is the electrons fill these orbitals from lower energy. So let me write it this way. Electrons fill orbitals from lower energy to higher energy. Okay, they're going into these spaces around the nucleus. So this one right here is going to get filled before this one does. And that one's going to get filled before this one does. So there's your order of filling. Okay. So how do we represent this? There's different ways. So let's use the box diagram. So I'm going to give the element carbon. This is element number 6. That means it has 6 protons, but it also has 6 electrons. And that's the key here. So the question is, where do these electrons go? So let me give you the order of filling. It goes in this order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. I'll stop right there. Now that's an order that I've memorized, but I wouldn't expect you to memorize that. That's a lot to memorize. So what I would recommend is when you do these problems, just have a card next to you with that particular order. There are ways to kind of memorize them, but to be honest with you, it's really not that necessary. Just have it there next to you. Many of the elements, you don't have to use all of these orbitals. So for example, carbon, we're not going to need to worry about these ones over here because carbon doesn't have enough electrons to fill those. Remember, it fills from lower energy to higher energy, but that's the order of filling. So 1s, 2s, 2p, 3s. The other thing you need to remember is that the s has, so let me write it here. Actually, let's do it this way. I'll make a little table for you. The type of orbital. And remember, we have 4, s, p, d, f. Then you have the number of orbitals. So this only has 1. This one has 3 orbitals. Remember, x, y, z. And then I said the d has 5 and the f has 7. Notice the pattern, 1, 3, 5, 7. Every time you go to a higher orbital, you increase L by 1, so you increase M sub L by plus or minus 1, so that gives you 2 more orbitals. So you have up to 7. And then there's 2 electrons per orbital. So the maximum number of electrons is twice the number of orbitals. So 2 times 1, which is 2. 3 times, 2 times 3, which is 6. 2 times 5, which is 10. 2 times 7, which is 14. So that's the maximum number of electrons that can fill these different subshells. So each subshell gets filled, and then you go to the next one. Okay? Till you run out of electrons. And if you get all the way up to 6p, that's a lot of electrons. You can start counting them up. Okay, so let's take carbon. Carbon is 6 electrons. So here's what you do. The notation is you use a box, a square, and then you write the name of the subshell underneath it. So 1s. Then you do the next one, the next subshell. So the next subshell has 3 boxes. The reason it has 3, shoot, that's not true. Getting ahead of myself. The next subshell has 1 box because it's the 2s. The next subshell, this one is a p, so it has 3 orbitals, so it has 3 boxes. And that's called 2p. So those are the names of the subshells. And then the boxes are representing the space in which the electrons occupy. Then we use arrows. Okay, so you can fit 2 electrons into each orbital. Okay, so let's do our 6 electrons. You do the first one, spin up, spin down. What happens is there's something called the Pauli exclusion principle. And what it says is the reason you can only have 2 electrons in an orbital is because no 2 electrons can be in the same orbital with the same spin. If one's spin up, the other one's got to be spin down. So if you could fit a 3rd electron in there, it would have the same spin as one of those 2, and that's impossible. So up to 2 electrons per orbital. So there's your first 2. Now we've got 4 more, right? Because you have a total of 6. Second one, spin up, spin down. So now we've used 2 more. That's 4 electrons. We got 2 more to go. Now here's what happens. In the subshell, all these orbitals are really at the same energy. So what the electrons do is they spread out over different orbitals. Okay, so if you're in the same subshell, put 1 electron into each orbital first, and then once they're all there, they each have 1. Then if you have more electrons, you can put spin down in the other orbitals. So this is called Huns Rule, which says that in a subshell, so these are different subshells. So once you get to this subshell, put 1 electron into each orbital, spin up, same spin, they have to be the same spin, and then that will do it. Okay, so that's the box diagram. 6 electrons, 2 of them are in the 1s, 2 of them are in the 2s, and 2 of them are in the 2p, 1 in each orbital. And that will determine the chemistry of this element. Carbon behaves the way it does because it has 2 electrons in that orbital, 2 in that one, and then 1 in each of those. That's going to determine what it reacts with, how it reacts with things, how reactive it is. Is it very reactive or only slightly reactive? Carbon is kind of an interesting element because of this distribution. Okay, so let's try another one. Let's try oxygen. Oxygen is element number 8. Okay, so you do that order, 1s, 2s, 2p. Now remember, we don't really need to use oops. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. We're not going to use all of these. We're only going to use a couple of them because we only have 8 electrons. Now, if you had 30 electrons, then you'd start going in that direction. So let's take a look here. 1s, 2s, 2p. And then remember the 2p, the p's have 3 orbitals. 1, 3, 5, 7. So SPDF, 1, 3, 5, 7. Now, we're not going to need it, but I'm going to draw the 3s just to show it to you. Okay. You got 8 electrons. So what you do is you fill up 1 subshell first. So 1, 2, spin up, spin down. These are called paired electrons. Electrons behave like little spinning magnets. So if one is spinning one way and the other one's spinning the opposite direction, they cancel each other. So overall, those electrons cancel each other's magnetization. This idea of MRI, if you've heard of that, these MRI scans in medicine, they're based on the magnetic spin of the electron, and protons also have spins. They're actually based on the spin of the protons in hydrogen. So then we got to get up to 8. 2s, spin up, spin down. So that's 4. Then you use Huns Rule. 5, 6, 7, what happens is putting two electrons in the same orbital, they repel each other because they're negatively charged. So they kind of want to be in different orbitals, different spaces around the nucleus. So 5, 6, 7, but now we've got one in each. So now the 8th one's got to go here. Okay, now arguably you could put it in here or here, but typically we put it in the first one on the left side. That's the notation we normally use. Okay, so there's your 8 electrons. Again, these ones right here don't have another electron in the same orbital. So these are called unpaired electrons. And so since electrons are spinning magnets, so this idea MS, right? Spinning magnetism, right? That's what it really means. S for spin, M for magnetism. Because those two are spinning in the same direction, it becomes additive. So overall, the oxygen atom behaves like a little magnet because there's no electrons to counter the spin, the magnetic spin that way. So it'll act like a little magnet. Not a real strong one, but a little magnet. Okay. Let's try one with more electrons. Let's try an iron atom. Now we're going to get up to some really big. Fe equals 26 electrons. Okay. Again, we're kind of ignoring the nucleus. The nucleus has its own dynamics of spin and all of that kind of stuff, but that's not that important for us right here. We're just worrying about the electrons because we want to do chemical bonding. So let's talk about iron. So iron has 26. So you're going to use quite a few of these subshells. So let's see. I'm going to draw a bunch of them. And then typically you put the P's together because they're in the same subshell. So that kind of represents that they're in the same subshell. They're connected to each other. Then you do 3s. I'm making them skinnier because I'm running out of room. And then you do 4s. I'm sorry, 4p. 3p, sorry. Words aren't the same. 1s, 2s, 2p, 3s, 3p. There you go. And then you have 4s. And then the next one's the 3D. 1. Oh man, we are out of room. So let me do this. Let me put it down here. I'm just going to say we're going to come down here. And we're going to do 3D. This one has 5. Remember, 1, 3, 5, 7. So the Ds have 5 orbitals. So that means you can fit up to 10 electrons in that particular subshell. Okay, so we got 26. So 1, 2, 3, 4. Remember, spin up, then spin down. That's the notation. You put the first one up and then the second one down. Then you do Huns Rule. In the same subshell, you go 1, 1, 1, 2, 2, 2. So that's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We're up to 20. Now we have a new subshell, 21. Again, these are all in the same subshell. So 21, 22, 23, 24, 25. And then you come back here and do 26. That's Huns Rule. Remember, spin up, spin up, spin up, spin up, spin up. So iron has 4 unpaired electrons. So it's a pretty strong little magnet. Right? This is called paramagnetism. Paramagnetism is the magnetism of an atom or a molecule that has unpaired electrons. And because iron has 4 unpaired electrons, it's a relatively strong little magnet, okay? Even at the atomic level. Now, take a look at that. See how this is getting pretty tedious. All these boxes, all these arrows. So what we do is we use a notation that's simpler. So instead of actually drawing every little box and every little arrow, we use a notation that's a lot quicker. And so the notation is called Electron Configurations. So these are box diagrams, but electron configurations are simpler. So here's what you do. You give the name of the subshell. So that first subshell is called 1s. Then you count how many electrons you put in it, and you write that as a superscript up above the s. So there's 2 electrons in the 1s, so we write that as 1s2. lowercase s, not uppercase. If you put uppercase, that's referring to something different. Then you go to the next subshell, 2s. How many are in there? 2. So you put a superscript 2. Then you go to the next subshell, 2p. So that's the name of the subshell. The number that are in there is up to 6. Looks like you got 6 there. So you can never have 2p7. You can only have 2p6 or lower. You could have 2p1 or 2 or 3 or 4 or 5. In fact, carbon is 2p1, but you can have up to 6 in the 2p subshell. Then you do the 3s. How many are in there? There's 2. Then you do the 3p. How many are in there? 6. Then you do the 4s, 2. And then the 3d looks like it has 6. No, wait a minute. 1, 2, 3, 4, 5, 6. Yes. Okay. And that would be the electron configuration. So that's a lot less involved. Not less involved. It's actually just as challenging and as difficult, but it's less tedious, I guess. Okay. It's short. It's a shorthand notation, essentially. So let me show you one more. Or maybe even 2. We'll see how much time we have. Okay, so let's do not the box diagram, but let's do the electron configuration. I'm going to pick a big one. I'm going to pick, let's do silver, which has 47 electrons. Okay, so what I would do is I'd say, okay, let's draw these out, 1s, 2s. I got to make sure I've got that on a card somewhere. Or memorize it. 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. I went a little bit further on that one, okay? We don't have to go that far. We only have 47 electrons. Now remember, S has 2 orbitals. I'm sorry, 1 orbital, and that's a maximum of 2 electrons. That's how many electrons. This is the number of orbitals. P has 3 orbitals, so that's 6 electrons. D has 5 orbitals, so that's 10 electrons. And then F has 7 orbitals, so that's 14, a maximum of 14 electrons. You can have less than 14. You can have 1. So here's what we do. We do the 1s. So we got 47 electrons. So 1s, that can go up to 2 electrons. Remember, we got to get up to 47. So then the next one is 2s. S can only have 2. Then we got to do 2p. That can have up to 6. Then we go to 3s. That can have up to 2. Then we got to get to 3p, and that can have up to 6. Then we got to get to 4s, and then that can have a maximum of 2. And then we got to get to 3d, and that can have a maximum of 10. So at this stage, you might say, well, am I getting close to 47? We're still a ways away from 47. Right here, it looks like we've got about 30. So we're getting closer. 4s, s can have 2. 3d. Oh, wait a minute. I already did 3d, sorry. Let's see, 4s. Oh, see, I made a mistake there. 3d is right here. The next one is 4p. I don't know what happened there. So 4p can go up to 6, right? P can do 6. And then you get 5s. S can have up to 2. And then the next one is 4d. Now we're getting close. We're almost there. I'm going to just count up. This is like a running total. 2, 4, 10, 12, 18, 20, 30, 36, right? I'm just adding those numbers, the superscripts. 38. Okay, so we're getting there. We're at 38. We got to get to 47. The D can handle up to 10. So that means we could go all the way up to 48 if we're just dealing with the 4D. but we don't need to go that way. We're only going up to 47. So that means we only need to fit 9 in there. So it's 4d9. Okay. So that's going to give you up to 47. So now we would say that silver, Ag, Argentinium, right? That particular element has 47 electrons. And if you take a look at what happens, the outermost electrons, are these ones over here, are in the 4d. And you got 9 in there. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Now, it turns out that there are a few elements that have wacky behavior. So silver was perhaps not the best example to show you. So this is called promotion, but it may come up on your homework or an exam. So there are certain elements, and I'm going to list them for you right here. Chromium, which is element number 24. Silver, which is copper. Copper, which is element number 29. Silver, which is element 47. And then gold, which is element number 79. These 4 elements have a very strange behavior, or a strange behavior, but it's just the reality. So what happens is all of those elements, the uppermost s electron subshell, so 5s2, 1 electron gets promoted to the d, to that outermost d, just 1 electron, never more than 1 electron. So what happens is chromium, you would expect it to be 3d, 4s to 3d4. That's what you would expect it to be. It goes to 4s1, 3d5. Copper, you would expect to be 4s2, 3d9. And what it does is it goes to 4s1, 3d10. Okay. Silver, you would expect to be 5s2, 4d, 5s2, 4d9. That's what you would expect it to be. That's what we got right here, for 5s2, 4d9. But what it does is promotion. So it goes to 5s1, 4d10. Okay, so notice the pattern. The chromium gets 5, half of the maximum. The copper and the silver get 10, the total maximum. Only 1 electron. And it's only for these elements. You don't have to worry about too many of them. And then the gold is right below silver. So it's 6s2, 5d9. That's what you would expect it to be, but it's actually 6x1, 5d10. Okay, so these 3 are all d10, s1. Again, it's just the outermost one. So it's not like you come over here and this one is doing it. That's not true. It's still 4s2. It's still 3s2. That's not changed. Just the outermost for those 4. And just so you know, copper, silver, and gold, those are all in the same column. So this is element 29, 47, and 79. You don't need to worry about it with the other elements that come before them, except for chromium. This is element 24, okay? That's called promotion, and that's really the only complication in this pattern. So we have 2 ways of doing this. We have the box diagram, and then you also have the electron configuration. And that should pretty much you should be able to get all of these done now. I've covered all of that. Yeah, looks good. So you're set, okay? So a lot of material in chapter 6, but once you get to these configurations, you will be set, okay? So reach out to me if you have any questions. I'll post this because I went through a lot of it very quickly, but I'll post it so if you want to watch it again. Should be up in an hour or so. And have a great day and a great weekend. But again, reach out to me if you have any questions.
Thank you, Professor.
Absolutely. Bye-bye.
Thank you.
Have a good day.
weekend.
Take care.